Before doing our next problem, we are going to review Kirchhoff's rules. Up to this point, we have been combining resistors in series and in parallel and using Ohm's law to find currents flowing in a circuit. Some circuits are just too complicated to do that, and this is an example of a circuit that is. We cannot simply combine these resistors in series and in parallel to find currents flowing in each part of this circuit. A technique to find the currents in a circuit as complicated as this were developed by Gustav Kirchhoff in the mid-19th century. This is known now as Kirchhoff's rules or Kirchhoff's laws. Before we look at these rules, we first want to define a few terms. A branch point is a point at which three or more conductors in a circuit meet. This is a branch point here. There is another branch point over here. A branch in a circuit is that part of a circuit between two branch points. This is a branch here, there is a branch here, and there is a branch down here. A loop is any closed path in a circuit. There is an upper loop here, there is a lower loop here, and there is also a loop in this path around the outside of the circuit. Kirchhoff's first rule says that at a branch point, the sum of the currents into a branch point is equal to the sum of the currents out of that branch point. Kirchhoff's second rule says that the algebraic sum of the EMFs around a closed loop is equal to the algebraic sum of the IR drops around that same closed loop. In using Kirchhoff's rules, we will follow a procedure. Step one in that procedure is to assign a current in each branch of the circuit and then apply the first rule that the sum of the currents in to a branch point is equal to the sum of the currents out. Let's do that in our circuit. Let's say that the current in this upper branch is flowing in this direction, and we will label it I1. In this branch, let's say the current is flowing in this direction, and we will label it I2. And in this lower branch, let's say that the current is flowing in this direction, and we will label it as I3. How do I know which way to draw these currents in? Well, the answer is I don't. I'm simply assuming a direction for these currents. If my assumption is wrong, then my final answer for these currents will come out to be negative, and it will tell me that I'm wrong. It is not necessary to spend time worrying about what direction the currents actually flow in. Simply assume a direction. You can't go wrong. The next thing we're going to do is apply the first rule that the sum of the currents into a branch point, say this branch point, is equal to the sum of the currents out. Well, going into that branch point is the current I2 and the current I3. Let's write the rule for that. I2 and I3 go in. The sum of them is equal to what comes out, which is the current I1. All right. Let's take a look at the second step in our procedure. Step 2 is to choose loops in the circuit and directions and apply the second rule that the sum of the EMFs around the loop is equal to the sum of the IR drops. We will apply this equation for each loop that we choose. Let's choose some loops. We have three choices. There is an upper loop here, a lower loop, and then a loop around the outside. I'm going to choose two of these three loops, the upper loop here, and I'm going to choose a direction to go around the loop as a clockwise direction. The lower loop, I'm also going to go around in a clockwise direction. Again, how do I choose the directions? The answer is pick any direction. You have a choice of two. You either go around clockwise or counterclockwise. It doesn't make any difference. I prefer to go clockwise. Next step is to apply the second rule that the sum of the EMFs around a closed loop is equal to the sum of the IR drops. One of the chief problems in applying this rule is keeping track of the algebraic signs of the EMFs and the IR drops. And there are rules to do that. The rule for the EMFs is that the EMFs are positive if they are passed through from the negative terminal to the positive terminal. If they're passed through in the opposite direction, then they are negative. The rule for the IR drops is that the IR drops are positive if a resistance is passed through in the same direction as the current. If it is passed through in the opposite direction as the current, then the IR drops are negative. Let's use those rules and apply Kirchhoff's second rule. Going around the upper loop, the sum of the EMFs, we encounter an EMF here, E1, and we have to determine its sign. Well, as we go through it in this clockwise direction, we are going from the positive to the negative terminal. Therefore, from our rule, that EMF is negative. Let's write that. Minus E1. There is another EMF that we encounter in this loop, E2. It also is passed through from positive to negative, so we should write it as minus E2. That's all of the EMFs. Now that is equal to the sum of the IR drops. The first resistance that we encounter is R1. We pass through it in this direction, which is opposite to the direction in which the current I1 flows through it. So it's going to be negative, and we're going to write minus I1 R1. The next resistance we encounter is R2. We pass through it in this direction. The current I2 is going in the opposite direction. It will be negative. So I2 times R2, again negative. That is all of the resistors in that loop, so that is our complete equation. Now we go to the next loop, the lower loop. As we go around it, we pass through the EMF E2 in the direction negative to positive. So by our rule, it will be positive. Plus E2 is equal to, and then the sum of the IR drops. We pass through R2 in the same direction as I2. So we write plus I2 times R2. Then we pass through R3 opposite to the direction of I3, and also through R4 in the opposite direction as I3. So we're going to write minus I3 R3 and minus I3 R4. These are our equations. In a typical Kirchhoff's rule problem, the known values will be the EMFs and the resistances. The unknowns will be the three currents, I2, I3, and I1. These are three equations involving three unknowns, and they are to be solved simultaneously to find the three unknown currents. Our next example problem will be an application of Kirchhoff's rules.